BA and PhD from the University of Cambridge in 1985 and 2000 respectively, and his research interests, which he'll be talking a lot more about tonight, are the characterization of the accumulating and eventually pathogenic molecular and cellular side effects of metabolism, what we call damage, that constitute mammalian aging, and designing interventions to repair and or obviate that damage. Aubrey deGrey is, as I told him on the car ride over here, one of my inspirations for being a biomedical engineer. I think his research is fascinating, so please join me in giving him a wide round welcome applause. Thanks, Dr. deGrey.
Great, thanks very much, Tal. I think my microphone is louder than Tal's, so you ought to be able to hear me, but I am rather hoping that band stops fairly soon. I will speak up, and if it becomes impractical, if you're just not really making out what I'm saying, then shake your fist and I'll stop until the band stops. Yeah, so this is my title. I'll be talking about a particular approach to combating aging, to developing medicine against aging, which I've been focused on for more than a decade now, and which is becoming quite realistic. It's coming to the attention of a lot of people, so I'm pretty happy about how things are going. I thought I would start by making sure that you know what I'm talking about when I talk about aging. Yeah, here they come. This is something that a lot of non-biologists get wrong. So I thought it was important to make sure that we're all on the same page with this. A lot of people think that dying from aging is what you'd like to happen in your life. That it means dying of natural causes, dying having escaped all of the horrible diseases of old age that we know that we don't want, like Alzheimer's and most cancers and cardiovascular disease and so on. So that's a colloquial definition of dying from aging. But from a biological perspective, it's nonsense. Because there's only one, even in principle, there can only be one reason why a disease should predominantly affect people who were born a long time ago and not affect young adults. And that is that it must be some aspect of the later stages of a process that goes on throughout life and that is initially harmless. And of course that process is aging. So logically, we need to include all of the diseases of old age as aspects of aging and as part of death from aging. And once you realize that, you get these unbelievable numbers. Out of the 150,000 people that die every day from aging worldwide, sorry, from all causes added together worldwide, 2/3 of them die of aging. And of course, in the industrialized world, where not many people die of malaria and so on, it's more like 90%. It's just unequivocally, obviously, humanity's worst problem. So that's why I work on it, really. Yeah, here they come. I think I probably really ought to stop for a couple of minutes while they come down the street, because they're just going to get louder. But yeah, think about that. Think about those numbers while I shut up. All right, I'll try and keep going. They stopped in the middle of the street, so I'll see what more I can do. All right, so I think I ought to point this out as well, actually. Even if you do have the good fortune to die of natural causes, it's not exactly what you want, really. What part of this is it hard to understand? It's pretty obvious that most people would rather be the person on the left, even if he is about to have his head bitten off by a shark. This is really why I work on this and why I think everyone ought to work on it. It's very important. Yeah, right. This is the organisation that I work for, as Tal mentioned at the beginning, Sense Foundation. We're a charity, a 501c3, so that's obviously a public charity registered in the USA. We're based up just north of here, actually, in Mountain View. And this is what we do. We're not in favour of aging. We're trying to do something about it. And in particular, we're trying to do this about it. We're trying to develop regenerative medicine solutions to the problems of aging. So I'm going to explain what those terms mean in a bit more detail, because it's actually quite important and quite easy to have divergent definitions of those terms. Wonderful, all right. Okay, so regenerative medicine and aging. I'm going to start with regenerative medicine. Now, I'm sure you've all heard of stem cell therapy, and you probably know that that's, a big part of regenerative medicine. Probably most of you have also heard of a field called tissue engineering, the creation of artificial organs, and that's also part of regenerative medicine. But most people actually, if you ask them what regenerative medicine is, they'll say, well, it's those two things and nothing else. And that's rather dangerous, because really, if one wants to think in terms of a definition, one needs to go a lot broader, in a couple of ways. So this is the definition I'm going to use tonight. And there's a couple of things I want to emphasize here. The first one is the type of damage that regenerative medicine seeks to fix. Most people think of regenerative medicine as being focused on acute injury, like, spinal cord trauma, something like that. And of course, that's a very important application of it. But there's no reason in principle why it shouldn't also be applied to the chronic, gradually accumulating damage that we see in aging. So that's really why this is a worthwhile thing to be thinking about. The other thing I want to mention is that the type of repair can be broader. So tissue engineering constitutes repairing the body by replacing a whole organ. Stem cell therapy is at the more microscopic level, repairing individual organs by replacing some of the cells in them. But one could go more microscopic than that. One could repair the internal structure of cells that are still in the body, that are alive but not working so well as they used to. Or, for that matter, one could repair the molecular structure of the material outside cells, the extracellular matrix, for example. And it turns out that all of that is very important when we look at the details of applying regenerative medicine to aging. Now, the definition of aging is even more fraught. There are loads and loads of definitions of aging out there. And most of them are pretty uncontroversial, they're definitely correct. But most of them are useless, or at least they're useless for the purposes of what we're here for tonight, namely for orienting our thoughts around how we might actually develop medicine against aging. So that's why I'm going to use this definition tonight. This definition is very good for orienting our thoughts around intervention. What I'm saying here is two key things. First of all, I'm saying metabolism eventually causes pathology. Okay, what does that mean? Metabolism is the word that biologists use to encompass all of the molecular and cellular and systemic processes that go on throughout life and keep us alive for as long as we do. It's not just oxidative metabolism. A lot of people misunderstand this because there's a phrase, metabolic rate, which means the rate at which oxygen is consumed by the body. And so people think of metabolism as simply oxygen consumption. But that's a very narrow definition, and the more strict definition that biologists use is the one I've just given you, covering the whole of metabolism. Pathology is the word I'm going to use to encompass all the things that go wrong late in life. So all the diseases of old age that you're all too familiar with, and also things that we wouldn't necessarily call diseases, but they're still bad for us, like decline in function of the immune system, for example, things that maybe predispose us to diseases. Okay, so metabolism eventually causes pathology. That's not very profound. It basically is just a sophisticated way of saying that aging is a side effect of being alive in the first place. But of course, in any mechanistic definition, you've got to more or less say that. The other thing is a bit more non-obvious, or at least a bit more important in this definition. I'm introducing this word damage. Essentially what this definition says is not only that metabolism causes pathology, but it says something about how metabolism causes pathology. The mediator of that process is this thing I'm calling damage. Damage is the set of intermediates between metabolism and pathology, the set of ongoing, lifelong side effects of metabolism that are created throughout life, even before we're born. But the key thing about damage is that it accumulates, because for whatever reason, these are molecular and cellular changes that the body does not simply reverse as and when they occur. So they progressively accumulate. And the reason why metabolism eventually causes pathology, but not initially, not in young adulthood, is because metabolism is set up to tolerate a certain amount of damage. But it's not set up to tolerate an infinite amount. So eventually the amount of damage accumulates to a level that exceeds the ability of metabolism to ignore it, and metabolism is impaired, and that's when the pathologies of aging start to emerge. Okay, so this is all very straightforward and simple and down to earth, but as you will see, it's very useful. Here's the first way of explaining why that definition is so useful. Here's my definition down the bottom. Metabolism causes damage, causes pathology. The first thing we can do is we can distinguish the two main schools of thought that have traditionally existed with regard to how we might develop medicine against aging. So as you see, I'm going to call those things the gerontology approach and the geriatrics approach. Right, now the geriatrics approach, what is that? Well, essentially it encompasses all of the medicines that we have today for the diseases of old age. It consists of essentially treating the diseases of old age just like any other disease, characterizing the symptoms, a little bit about the causes maybe, and attacking the disease head-on, one disease at a time. That's what geriatrics is all about. And there's a big problem with it, and that problem is made very crystal clear by this definition of aging. The problem is we're intervening too late in the chain of events. The target of the geriatrics approach, these pathologies here, is being driven by this accumulating damage, which means that the geriatrician's job is getting harder and harder as the patient gets older, because the damage is getting to a higher level of abundance and pushing the pathologies forward more and more aggressively. So this tells us immediately that the geriatrics approach, yes, it's better than nothing, but it's not much better than nothing, and it never, even in principle, can be much better than nothing. It's just too late in the chain of events. There's a downward spiral, a losing battle that the geriatrician is facing. Okay, now I'm certainly not the first person to have made that observation, though I may be saying it in a new way. A lot of people have been realizing this for a long time. And that's why they've been interested in this other approach, the gerontology approach. And what that says is, well, maybe prevention is better than cure. Maybe if we intervene at an earlier stage in the chain of events, we'll have a better chance of doing serious damage to this thing aging. So the idea here is, let's not worry about all this lot. Let's instead intervene back at the beginning of the process and clean up metabolism. Let's try, in other words, reduce the rate at which it creates these various types of damage in the first place, so that, of course, we then postpone the age at which damage gets to a pathogenic level. And that's, clearly a good idea in principle as well. It doesn't have this intrinsic limitation that I've described with the geriatrics approach. Unfortunately, it does have another limitation, a rather profound one. Metabolism is extremely complicated. This is, as the biologists among you will know, a simplified diagram of a small subset of what we know about how metabolism works. This is a biochemical chart. And that's bad enough. As you can see, it's really rather hairy. But that's not the main problem. The main problem, and again, any biologist will agree with me on this, is that this is a simplified diagram of a small subset of what we know about how metabolism works, which is completely dwarfed by the utterly astronomical amount that we don't know about how metabolism works, even ignoring all the stuff that we don't even know that we don't know. So, it's completely hopeless. In principle, the gerontology approach could help us to significantly, substantially postpone the ill health of old age. But in practice, it just ain't going to happen. It's an idea whose time has absolutely not come. Because with a system like this, that's so complicated and about which we are so profoundly ignorant, there is just no way that we can significantly tune it up without doing more harm than good by having unintended side effects of whatever we do. So that's all rather miserable, but if that were the end of my story, I wouldn't be standing here, obviously, so there's got to be more. In order to introduce the basic idea that I'm going to be talking about for the rest of tonight, I want to briefly digress into an analogy. I'm going to say a few words about cars. So, your average car might last, 10 or 15 years before you junk it and get a new one. This car's more than 50 years old. That's pretty good for a car. And the reason it's 50 years old is, of course, because it was built that way, with, corrosion-resistant metal and really tough tires and all those good things. And that's very much the same reason why the human body lasts as long as it does, lasts so much longer than the body of, let's say, a dog or a mouse. We're just built better. We've got more thorough, more comprehensive anti-aging machinery built into us than what these shorter-lived animals have. That's really the fundamental reason why we live longer than they do. But actually, the important thing about this slide is not the picture. The important thing about this slide is the title and the fact that I've talked about another type of car up at the top there. The reason I've talked about VW bugs is because there are just as many 50-year-old VW bugs driving around the streets of this world as there are 50-year-old Land Rovers. Here's one. This was built in the same year as the one on the previous slide. And it's doing very nicely. And of course, it's not doing very nicely because it was built that way. You know, the warranty period on a Land Rover is about 50 years probably, but the warranty period on a VW bug certainly isn't. So, what gives? How does this come about? The answer, of course, is maintenance. VW bugs do have something going for them. They've got style, their owners fall in love with them, and they do an unusually comprehensive job of maintenance, of preventative maintenance on them to keep them in good condition. And that, as you can see, it works. If maintenance is sufficiently comprehensive, then it can keep a machine going far beyond the duration, the lifespan that it was designed to have. Now, of course, a car is only a simple man-made machine, but, you know, the human body is also a machine. Granted, it's much more complicated, but that's only a difference of degree. So, in principle, this rather suggests that we might be able to maintain the human body way beyond its warranty period just by doing sufficiently comprehensive maintenance. And that's what I'm going to be talking about from now on. This third, completely different approach, which again we can describe using that definition of aging that I put up at the beginning of the talk, and which distinguishes itself from the other two in this rather obvious way. Rather than trying to slow down this process here where damage causes pathology, or this process where metabolism causes damage, instead, the idea here is to uncouple those processes from each other, to separate them, so by going in and periodically repairing these various types of damage before they get to a level of abundance that's pathogenic. Now, this, I think, has a much, much better chance of success in the foreseeable future than either of the other approaches. First of all, it's preemptive enough to avoid this downward spiral that I explained for the geriatrics approach. Damage, by definition, does not have any accumulating precursors, because damage is the set of ongoing, lifelong side effects of metabolism. So the problem isn't intrinsically getting harder as the patient gets older. Secondly, and perhaps even more importantly, what we're doing here is we're saying let's leave metabolism alone. Let's let metabolism create damage at the rate that it naturally does so. And let's simply interfere with that damage and get rid of it periodically after it's been created, but before it's risen to the level of abundance that's bad for us. And by that means, what we're effectively doing is sidestepping all of our ignorance about metabolism. If we don't have to interfere in metabolism, then we don't really have to understand very much about how metabolism creates damage. We just have to characterize the damage itself, and then, of course, figure out ways to repair it. So that's the idea of the maintenance approach to combating aging that I've been following for the past decade or more. Right, I put this into a talk I gave about a month ago, and it's something that a lot of engineers, especially students, are interested in, so I thought I'd talk about it here as well. Hand up anyone who actually knows what cryonics is. All right, a few of you, very good. So for those of you who don't, cryonics is all about freezing people directly after they've died. Now, of course, what I'm talking about here is being legally dead. In other words, someone who is qualified to do so has pronounced that you're dead. But from a biological perspective, death is not an instantaneous phenomenon like legal death is. The only reason we have this concept of legal death is because, as a society, we seem to be more comfortable with people being either alive or dead and not somewhere in between. But from a biological perspective, what death is about is simply a process of decay to an irreversible point. When your heart stops, the gradual decay that was happening throughout the previous years speeds up very greatly because starvation of oxygen from various tissues causes them to get in trouble. But even though it speeds up, it doesn't speed up to an infinite speed. So it's possible to arrest that decay immediately after the heart stops without much further decay having occurred. and lowering the temperature of the human body to minus 196 degrees centigrade, which is liquid nitrogen temperature, is a very good way of doing that. So cryonics is all about doing that. The motivation, of course, is that, in principle, we ought, in the future, to have a chance, anyway, of developing medicine that can restore someone who's only just legally dead to a state of health again. And the reason I mention it in this talk is because doing that is really just a natural extension of the medical research that I'm going to be talking about for the rest of the evening. It's just a matter of repair at the molecular and cellular level. It's just that it's repairing a body that's a bit more damaged than someone whose heart is still beating. So I think cryonics is actually very realistic. I think that it's something that needs a great deal more support. And if anyone tells you that it's science fiction, you can tell them they're wrong. It's definitely science foreseeable in my view. We don't know that it's going to work, obviously not. But we think, but there's good reason to believe that it very well may. The technical difficulties in minimizing the damage done to the body by the process of actually freezing them are being addressed very, very aggressively in research going on, especially in the USA. So, and I happen to know a lot of the people who are doing that research. So I think there's great reason for optimism about cryonics. All right, enough about that. It's probably time that I told you what damage actually is in a proper, down-to-earth, physical, proper way. Those of you in the audience who are biologists will probably have been a bit nervous that so far I've described this word damage, in terms of its role in aging, but I haven't told you what it actually is in practical terms. So now's the time for me to tell you about that. And the big news here, the big piece of good news, is that really got this whole research field going when I started talking about it about a decade ago, is that it seems we can actually enumerate all of the different types of molecular and cellular change that occur that qualify as damage by the definition I'm using today. We can classify them into just 7 broad categories. Here are the categories on the left-hand side of this table. So, of course, as you can see, these things are actually proper, bona fide, real biological phenomena. Cell loss, that's just cells dying and not being automatically replaced by the division and differentiation of other cells. And clearly that does happen during aging. The most conspicuous example of it is probably Parkinson's disease, where a particular part of the brain, called the substantia nigra, undergoes an unusually rapid rate of death of a certain type of neuron that makes a chemical called dopamine, and you get the symptoms of Parkinson's disease. But there are plenty of other parts of the body which also exhibit cell loss. I mentioned extracellular junk as the next item. That's something that we see in Alzheimer's disease. What is junk? It's simply molecular byproducts of normal essential metabolic processes that, for whatever reason, the body does not have the ability either to break down or to excrete. So that junk simply accumulates, and it accumulates both inside and outside the cell. I mentioned junk inside the cell down here. Here's junk outside the cell. That's another example. Another thing that happens outside the cell is as molecular changes to the extracellular matrix that I mentioned earlier. The extracellular matrix is a lattice of proteins that holds our tissues together in the shape that they normally are. The extracellular matrix needs to be elastic, especially certain parts of it, like the walls of our arteries, and that elasticity diminishes with aging because of chemical changes that make new covalent bonds between proteins. Sometimes cells get into a state where you've got too many of them because they're not dying when they're supposed to. There are certain cases in the body where cells are supposed to die, and sometimes they get into a state where they're no longer receptive to the signals telling them to do so, and we get too many of them, and that causes problems. The immune system suffers that way, it turns out. Almost all of you probably know that not all of our DNA is in our chromosomes. Some of it is in this special part of the cell called the mitochondrion, which is responsible for a number of very important aspects of metabolism, including, in particular, the chemistry of breathing, the combining of oxygen with nutrients to extract energy from those nutrients. The mitochondrion is the only part of the cell that has its own DNA, and that DNA accumulates mutations, which seem to be bad for us. As I mentioned, molecular garbage accumulates inside the cell as well as outside. And finally, there's mutations in the nucleus, and there are good reasons to believe that the only real effect of that really we need to worry about in a normal lifetime is cancer, which is, of course, the other way of having too many cells. Rather than having cells not dying when they're supposed to, this is a case of having cells proliferating when they're not supposed to. Okay, so that's pretty good news, that we can actually describe the problem in this very clear classification into this handful of different types of damage. Now, of course, I'm not saying that that means that aging is simple. Each of these categories encompasses quite a number of different examples, but, in different types of change in different tissues. But still, it's a good start. And we have very good reason to believe that this really is an exhaustive classification. One thing is that simply it hasn't expanded for nearly 30 years. All of these 7 things have been studied extensively by gerontologists for nearly 30 years, since the early 1980s, in some cases a lot longer ago than that. And, we've come a long way since then in our ability to analyze biological systems. We really ought to have found some more if there were any more to be found. But the really good news is, of course, the existence of the right-hand column on this table. The fact that we can talk about ways to actually repair this damage in each case. And I've obviously just put a one-line description of each of the fixes on this slide. But what you need to know is that we can actually describe these prospective fixes in a very great deal of detail already. The book that I read a few years ago on all of this has an entire chapter dedicated to each of these 7 types of damage and how we might go about fixing them. So that tells you how much detail. As engineers and technologists, you all appreciate, I'm sure, that the level of detail with which we can describe a potential solution to a technological problem is absolutely critical to one's entitlement to optimism about, for example, how long it's going to take to actually implement that solution. So this is very good news. And I'll be talking about some of these solutions later on. I'll just start with the top one, which is cell therapy. Of course, I mentioned stem cell therapy earlier as a key component of regenerative medicine. That's what stem cell therapy is. It's simply reversing loss of cells, putting cells back when the body is not automatically doing it itself. And the other things down here, I'll go through some of them at least in more detail. One thing that I want to emphasize before I go on is how close all of this is. Some of these things are at a pretty early stage, and I think it may be as much as 25 years before we get them working in humans. And even that, of course, is only an estimate. I think we have a 50-50 chance of getting all of this working in 25 years. But as for anything that's that far away, any prediction is very speculative. I know that there's at least a 10% chance that it could be 100 years if we just have underestimated the difficulty of the problem. That's okay, of course. A 50% chance is quite enough to be worth fighting for. But some of these things are a lot closer than that. I've highlighted the first 2 here because those 2 are already in clinical trials. There are clinical trials of stem cell therapies, quite a lot of them going on around the world, including for conditions associated with aging. There is indeed a stem cell therapy trial going on for Parkinson's disease. The junk in the gaps between our cells is something that is usually called amyloid, and the most well-known example of it is in Alzheimer's disease. There is already a phase 3 trial, actually, the last phase before regulatory approval, going on right now to test an approach to getting rid of this amyloid using vaccination, basically. I can talk about that later if anyone's interested. Now, the other ones, as I say, are a lot further off, but still, progress is being made. I thought I would mention this one briefly, death-resistant cells that have forgotten how to die when they should, because there was a paper came out not long ago, only about a month or 2 ago, that constituted a very big step forward in that area. I'm actually going to show you some of it here. Cells that get into this death-resistant state tend to overexpress a gene called P16, and they can be induced to accumulate at an accelerated rate by certain genetic modifications that you can make to mice. So what this group in upstate New York did was they made some mice that had this accelerated accumulation of this particular type of death-resistant cell. But they did another tricky thing to these mice genetically. they prepared them so that by giving them a drug at some point, you could quickly kill all of the cells that were overexpressing this particular gene. That's a relatively straightforward routine trick that you can do with mice in the lab. But what was interesting was the effects. So with this accelerated accumulation of these death-resistant cells, these mice don't live very long. The average mouse might live a couple of years. These ones live less than a year. They live about 10 or 11 months. So the bottom mouse here is a mouse that's about to die. It's 10 months old, and as you can see, it's extremely unhappy, and that's because it's got all these cells. The mouse above, which as you can see looks perfectly normal and happy, has the same initial problem, but at the age of 5 months, what the researchers did was they introduced this drug I mentioned, which killed off all of the cells of this nasty type. And as you can see, the mouse was extremely happy. This on the right-hand side of the graph, one of a dozen or more graphs in this paper looking at all manner of aspects of aging and showing how the mouse that had the drug was protected against these things. This one, they were looking at the diameter of muscle fibers, which is something that matters a lot in aging. So, yeah, it was a very cool study. It got lots of press, and so it should have done, because it really showed that, first of all, cells like this are bad for you in a lot of interesting ways, and secondly, that if you get rid of them, you really can eliminate the consequences of having those things, even if you do so in adulthood. In this case, it was done at 5 months of age. So that's pretty good news. Going back to the list, though, the one that I'm going to spend a bit more time on is this one down here, junk inside cells. The reason I'm going to do that is, first of all, unlike the things I've mentioned so far, this is work that's actually happening in our lab at Sense Foundation in Mountain View. And the second reason is because it's just very cool and glamorous and you're going to like it. So here's an example of the problem that we want to solve. You'll probably all know that the #1 killer in the Western world is cardiovascular disease. And what happens basically in cardiovascular disease is you have the accumulation of fatty material in the major arteries, which eventually starts to fragment and flow around, and that's how you get heart attacks and strokes, when bits of fatty junk get stuck in smaller blood vessels. But it all starts very gently. In fact, very early in life. You can see the first stages of this in kids. What happens is that stuff that is naturally and, for good reasons, being transported around in the blood, occasionally gets stuck in the artery walls. And this detritus that gets stuck needs to be got rid of, needs to be hoovered up, and there is a particular type of white blood cell called a macrophage that goes into the artery wall for that purpose. It basically engulfs this detritus and breaks it down and processes it and chucks it out again in a healthy form. Unfortunately, some of this detritus is contaminated with material that the macrophage doesn't know how to process. So gradually, these macrophages that are sitting in the artery wall doing their thing get poisoned. And they get into this state that you can see here. This is a sort of undead macrophage called a foam cell, which is full of stuff that it used to be able to process, but it has lost the ability to process it because of this toxicity I mentioned. Essentially, the toxins are predominantly oxidized derivatives of cholesterol. Cholesterol itself, you may think cholesterol is a bad thing. No, cholesterol is a great molecule. We need it, we need a lot of it, and the body knows how to handle it. The problem is that it gets oxidatively modified sometimes into forms that we don't know how to handle. And this is the result. This is the first microscopically visible stage of atherosclerosis. What happens is that you get more and more of these cells, eventually they start causing inflammation, and you get a proper atherosclerotic plaque, which is of course the thing that grows and eventually gives you a heart attack and a stroke. All right, what can we do about it? Well, around about 1999, I made a rather unlikely proposal. I said, let's try and use some technology from a completely different part of biology, from something that's never been used for medicine in the past at all. It's only been used in an area, in a completely different area, namely environmental decontamination. So there's a field called bioremediation, which was invented back in the 1950s actually, And nobody really thought it was going to work until about the 1970s, but I assure you it does. Bioremediation is all about finding bacteria that can break down pollutants. It turns out that a lot of pollutants are organic molecules that are energy rich. So if you're a bacterium and you know how to break them down, then you can live off them. And then that means, of course, that there is selective pressure on the microbial ecology in a polluted environment to develop the genetic machinery to break down the pollutant. Turns out this actually works. Evolution is damn clever, and bacteria exist that can break down God knows what. TNT, dioxins, rubber, plastics. It's incredible. What I realized was that the molecules that poison cells in the way that I just described for atherosclerosis, and also in a different way for macular degeneration and for various other diseases of old age, these toxins are also energy-rich molecules. And graveyards don't accumulate them. Graveyards accumulate certain aspects of human remains, obviously, bones and teeth, which, of course, are not energy-rich. It's no point if you're a bacterium trying to break down bones and teeth. But they don't accumulate stuff like this. So I realized that maybe what's going on is you've got this process in the human body that turns young people into old people, and then eventually into dead people. And then you've got this completely different process going on in the soil after people are buried that turns dead people into decomposed people. And that process is mediated by the microbes in the soil. And so all we have to do is figure out how those microbes are doing that. Figure out the genes, the genetic basis for that ability, and then maybe we'll be able to apply that information, the genetic knowledge, to our own cells, introduce new genes into our own cells. This is my totally horrible cartoon of a neuron. And thereby counteract the initial process that turned young people into old people in the first place. Crazy idea. Well, it turns out it seems quite promising. Here's the first step. We've got to find bacteria that can actually break down substances of interest. So the substance of interest for this experiment is 7-ketocholesterol, which turns out to be public enemy number 1 in atherosclerosis. There's lots and lots of different oxidation derivatives of cholesterol that we find in atherosclerotic plaques, but this one's the worst in terms of abundance and toxicity. So what you've got here is 7 strains of bacteria that are being given a bunch of 7-ketocholesterol to eat, and they're not being given anything else. So if they can't eat this stuff, then they can't grow. And in the case of 5 of those strains, that's exactly what happened. They just sat there like lemons doing nothing. But the other 2, as you can see, had a while of a time, and after only 10 days, the material's gone. You don't even need a microscope to see the result. So this is very cool. We can find bacteria that can break down substances that accumulate toxically in the human body. Then what you've got to do, as I mentioned, you've got to figure out how they're doing it. You've got to find the genes and enzymes involved. There's various tricks for doing that. This is one. It's called mass spectrometry. Essentially what we're doing here is identifying the breakdown products, the things that the bacteria create in the process of destroying the material. And when we do that, we can infer what the enzymatic reaction is that's occurred, that's got rid of the molecule, and from there we can use bioinformatics, basically, to identify candidate genes. That has worked very well in our hands, and the result is we've got, and a couple of other approaches have also worked, the result is we've got several genes now, enzymes that can break down 7-ketocholesterol. We've also got several that can break down the counterpart, the equivalent molecule that's the major culprit in macular degeneration, the main cause of blindness in the elderly. So this is great. We can do this. The next step is a bit more complicated. I wanted to mention, first of all, it's not necessarily that we have to break the substance down. Remember I mentioned early on that the problem of accumulation of molecular garbage, whether inside or outside the cell, is that the body can do neither of 2 things. Neither can it break the substance down, nor can it excrete it. So another alternative, in other words, that we have is we can simply stimulate excretion of the offending molecule. And some of these tricks turn out to do that. You might want to do things that just make it easier for the cell to get rid of the material. But the main thing we've got to do is modify the molecule. So that means we have to get our new enzyme into the vicinity of the molecule. And that's not necessarily very easy. A bacterial cell is really simple, whereas a mammalian cell, a human cell, has lots of compartments. So we have to do some clever tricks to our genes to make sure that the protein goes to the right part of the cell, which is usually somewhere called the lysosome. And this is just showing that we can do that. The left-hand side shows a stain for the lysosome. Those are the lysosomes in a bunch of cells. This is a stain showing our engineered gene, and this overlay just shows that more or less the protein's going to the right place. So that's good news. But then, of course, even that doesn't guarantee that the enzyme's still going to work, because the pH is different than it was in the bacterial cell, things like that. However, the good news is, and I emphasize this is very preliminary data, this is unpublished because we've only done it once or twice so far, but we're very happy about how things are going here. What this is basically showing is that we can actually protect cells. Essentially, the y-axis here is a measure of viability of cells. On the x-axis, we've got a bunch of different concentrations of 7-ketoglycerol, this nasty stuff. And what this is basically saying is that if you've got a humongous amount of the toxin, then the cells still die because the enzyme can't work fast enough. But if you have a more modest amount, then the cells do a lot better, the right-hand column here, than if you do some negative control, like, for example, just giving the stuff to cells that don't have the engineered gene, or they have it but it's targeted to the wrong part of the cell, or whatever. Those are all these other bars. Okay, so this is pretty good news. We do seem to be getting somewhere. But I do want to emphasize that I'm not trying to tell you this is easy. What I've shown you in the past few minutes is steps 1 through 4 of this project. We're very good at finding bacteria that do what we want. We're very good at finding out how they do it. We're getting fairly good at getting that function to work in cell culture in the laboratory. But of course the next step is to get it to work in live animals, in mice in particular. And that's going to take a little while. It's not trivial doing that, because we've got to worry about all manner of side effects that we might have. The enzymes breaking down things that we didn't want them to, stuff like that. So we've got a few years of work still to do to get this thing really working properly in a living organism, I think. And it's only then that we can even start doing clinical trials. So this is a long, big, ambitious project. But that's what Sense Foundation does. We're not scared of big, ambitious projects. In fact, we have positioned ourselves precisely to do things that most scientists are too cowardly to try. Because if nobody does them, then in the long run, things are going to go too slowly. Sure, we need to do the easy things as quickly as we can, but we also need to make baby steps towards the really hard things that are going to take a very long time to actually get to work, or otherwise, in the long run, we're just not going to make much progress. At the moment, as I'm sure you're aware, we just don't have effective treatments for heart disease or for macular degeneration and so on. That's because, they are genuinely very tricky problems. And nothing is coming down the pike either. We're not going to have significantly more effective treatments 2 or 3 or 5 years from now either. So the sooner we start these very ambitious, very out-of-the-box approaches to combating these things, the sooner we will have real treatments. And that's what Sense Foundation is all about. All right, for the last 10 minutes or so, what I'm going to do is talk about the longer term. All of you are technologists, and I know that technologists like this part of the story, so I'm going to spend a little time on it. What I've said here is that we ought to be able to fix all of these things, and this is all we need to fix. So you may be a little bit suspicious by what I'm saying at the top here, that I'm saying that what we will achieve is just 30 years of additional healthy life. And that's what I've defined using this term, robust human rejuvenation. Now 30 years, of course, that's nothing to sneeze at, that's great, but it's not like, vintage cars which seem to be able to go on absolutely forever. So what's the catch? Well, the catch is that these therapies won't be perfect. These therapies will work fairly well on their respective type of damage, but there will be a residual, difficult subset of each of these types of damage that the therapies just won't work on. So that means that eventually you're going to get sick anyway. But it turns out that that's not quite the end of the story. I told you earlier on that what I call the gerontology approach, slowing aging down, is basically a non-starter for the foreseeable future because metabolism is just too complicated for us to be able to intervene in a way that really does slow down the creation of damage without doing more harm than good in unforeseen ways. But supposing we could do it, it turns out that even if we could do it, it wouldn't be nearly so valuable as repairing damage in the way that I've been describing over the past 20 minutes or so. This is what you get if you start slowing down aging. Let's call it, no, just, I'm obviously being very schematic and formalized here. Don't take too much quantitation out of this. What I'm saying here is basically, if we slow down aging by a factor of 2, then this is the sort of thing we get. I've got, obviously, age on the x-axis. On the y-axis, I'm using the word reserve, but that's just the reciprocal of damage. It's like the amount of additional damage that you can afford to accumulate before things start going seriously wrong, before pathology starts to emerge. So the red line then simply shows normal aging. You start off at age 0 with not much damage, lots of reserve. Aging happens, time goes by, you accumulate damage, your reserve goes down, eventually you hit this dotted line called the frailty threshold, and that's when pathology starts and you are not long for this world. The blue line denotes what happens if you start at this age slowing aging down, and you get an increased healthy lifespan. Of course, eventually you get to the frailty threshold anyway, and then the therapies don't really work very well after that because pathology spins out of control in the way that I explained at the beginning of the talk. So that's all right. Problem is, of course, you've got to start fairly early. If you happen to have the misfortune to be already 60 when these therapies are developed, then you're not going to be in that situation. You're going to be in this situation, where you only get the therapies when you haven't got long to go before getting to the pathologies of old age. And if that happens, then your additional healthy life is much less than the additional healthy life that you would have had if you'd been able to start earlier. So that's a bit of a shame. You might be able to do a little bit better if we carry on improving the therapies. So here what I'm showing, the yellow line is the situation for a 60-year-old who just gets these therapies. The green line is a situation where they get the therapies, but before they get frail, when they're still, let's say, 70 and biologically 65 or something, then we improve the therapies another bit. We make them slow down aging by a factor of 4 rather than only a factor of 2. And then, of course, as you see, you get an extra increment of healthy life before you hit that frailty threshold. All well and good, but it's still not as good as if you'd been able to start the therapy at age 30. Now, however, let's think a bit more about repairing aging. The pink line here is what's going on if you repair aging. And here what I'm doing is I'm comparing therapies of the same quality. So the yellow line is when you start at age 60, halving the rate of aging, and the pink line is when you start at age 60, repairing half of aging, half the damage of aging. As you can see, it's very much more effective. You end up fixing half the damage, then aging carries on at the normal rate because, of course, you're not slowing down aging with these therapies, but you can apply the therapy repeatedly. It has less and less effect each time because the difficult damage is continuing to accumulate unabated because the therapy doesn't work on it, and so eventually you get tipped over the frailty threshold, but you did one hell of a lot better than if you'd only slowed aging down. So this is all pretty good news. This is another reason why the maintenance approach is such a good idea. It's not just that it's actually easier to implement, it's that if we do implement it to a certain quality, we get much more bang for our buck. But here's the really interesting thing. Remember a moment ago I told you that you might be able to get a little more extra life if you carry on improving the therapies, if you knock back the rate of aging by an extra increment before the patient gets frail. Well, now let's apply that same principle to the maintenance approach, to the repair of aging. It's a little bit dramatic. This is what you get, if you think about it. Here what we got is our hero comes in, they get a rejuvenation. Next time they come in, the therapies have been improved, and the therapy no longer just fixes the easy damage, it fixes half of what used to be the difficult, irreparable damage. Third time, they fix another half, and so on. And as you can see, the difference is not just a difference of degree, the way it is with the difference between the yellow and green lines. Here what we've got is people over the long term getting biologically younger as they're getting chronologically older. People are actually moving away from that frailty threshold, however long they live, because the therapies are being improved faster than time is passing. The idea is staying one step ahead of the problem. You know, this line just doesn't get anywhere near the frailty threshold, however long the person lives. So in this scenario, people genuinely can live indefinitely in a truly youthful state, just like you folks out there. Genuinely indefinitely. And that's why those of you who are aware of my work will be aware that I talk about people who are alive today very probably living 4-digit lifespans, if not more. Because that's how long we would live if we didn't have aging. That's, you know, if you think about the half-life of someone who stays as likely to die each year as they are in their 20s, you know, when you reach your 26th birthday, your chance of not reaching your 27th birthday is very low. It's less than 1 in 1,000. So the half-life, therefore, of course, is in 4 digits. Okay, so this is pretty amazing. But there's a catch, of course. The thing is, we do have to improve the therapies fast enough. If we only improve the therapies a little bit each time, then the result would be a further extension of healthy life, but not an indefinite extension. So we've got to improve the therapies fast enough. There's a critical rate of improvement that is required. And that's such an important concept that I gave it a name. I call it longevity escape velocity. This is what it comes down to in words. It's the rate at which these rejuvenation therapies need to be improved following that first step where we get maybe 30 years of extra life in order to stay one step ahead of the problem. Okay, so in words it obviously looks very complicated, but as you've seen, it's a very simple concept when you've seen it drawn out. So the question then is, are we actually going to achieve longevity escape velocity? Is it likely that we will be improving these therapies fast enough to stay one step ahead of the problem? Well, there's various ways to think about that question. One way is to look at recent technologies of other types and say, well, how fast did we do things then? And, you know, it's looking pretty good if you think about, for example, the rate of improvement of powered flight or computers or whatever. But let's do a more direct approach. Let's look at the aging itself in the only way we can, namely with a computer simulation. I did this a few years ago. Took the definition of aging that I've been using all evening, and I said, well, okay, let's impose on that these interventions, introduced, first of all, imperfectly and progressively improved on a reasonable schedule. And this is the bottom line. This is all published, so if anyone wants, you know, copies of the paper, you're obviously welcome to email me. But here what we did was we did the simulation, and the result here is shown as survival curves. Okay, so a survival curve is a very simple thing. It's simply a graph of showing what proportion of an initial population of individuals is still alive at any given age. So the black line here on the left is not simulation. The black line is actual data from, I think, actually US 1999, something like that. And what we're showing here is, of course, everyone's alive at age 0 by definition. Not many people die until they're age 50 or 60, then they start dropping like flies and hardly anyone gets past 100. Okay, so you knew that. Right, what are these other lines? The other lines are simulations. Let's take this dark blue line first. That dark blue line is a simulated survival curve of a population in which the risk of death at any given age is intrinsically the same as for the black line, but these people are getting those therapies. But they're only getting them starting from the age of 80. All right, so that's of course why the two lines are coincident until about halfway down, because half the people are dead by the age of 80. After that, as you can see, there's some benefit, but very little benefit. And that's something I want to spend a moment on, because it's very important to remember that this is all about health. We are not going to be keeping people alive in a bad state of health. Once you hit the frailty threshold, you're a goner anyway. What we're going to be doing is keeping people from getting there. And so, of course, if people are already in a fairly bad way before the therapies come along, then it's a tall order pulling them back from the brink with these initially imperfect therapies. And that's why these people continue to have a relatively high risk of death each year for a fairly long time, and therefore none of them, just probabilistically, none of them get out the back. None of them get more than 10 or 15 years of extra life. But now let's look at some of the other lines. Let's look at this line here, this grey-blue line. That is the simulation in which, again, the population is intrinsically at the same risk of death at any given age that the black line shows, but this time they're getting these therapies starting 10 years earlier than the blue line, at the age of 70. So the story is pretty much the same at first, not a lot of improvement, but eventually the therapies start getting the upper hand. You start getting these people genuinely being pulled back and becoming biologically younger, and the risk of death, of course, correspondingly going down. and eventually you've got maybe 10 or 15% of these people coming out to the age of maybe 150, by which point the risk of death from anything to do with aging has become pretty much negligible. These graphs, incidentally, don't show anything to do with deaths from causes other than aging. If you're 60 when the therapies start, that's the brown line, and nearly half the people get out there. Now, that's pretty good. I mean, that is unequivocally longevity escape velocity. That's what we're talking about. But really, the most important thing about this slide is this up here. In this particular run of the simulation, I was just ludicrously, insanely, ridiculously over-pessimistic about the rate at which the therapies would be improved. What I said was, let's presume that they double in their effectiveness only every 42 years. Now, I mean, come on, how crazy is that? 42 years. I mentioned powered flight a few minutes ago. If you think about it, powered flight, 42 years is the time between when Lindbergh first flew solo across the Atlantic and when Concorde first flew across the Atlantic. That's the amount of difference that we've had in the 20th century in 42 years in another technology. And of course, things are moving faster in the 21st century anyway. So it's totally ridiculous to suppose that we would go that slowly in improving these therapies once we get this first initial breakthrough that gives us maybe 30 years of extra life. But even if we did go that slowly, we'd still got longevity escape velocity. So what this tells us is, once we've got those first rejuvenation therapies that give us a couple of decades of extra life, we've done the hard part. It's a very counterintuitive result, but it's completely inescapable. That it is vanishingly unlikely that we will fail to achieve and maintain longevity escape velocity once we get that initial breakthrough. So that's why I end up being able to say things like this. We don't know how long it's going to be before we get that initial set of therapies. I said earlier on that I think we've got a 50% chance of getting there within maybe 25 years, but that we've got at least a 10% chance of not getting there for 100 years. That's just how it is with fundamental breakthroughs. You all knew that. But once we do get there, game over. We've done the hard part. So that's why we can say this bottom thing down here, that almost certainly the first person to live to 1,000 is less than 20 years younger than the first person to live to 150. 150, incidentally, for anyone who's not aware, is chosen simply because that is about 30 years longer than the current world record longevity of 122. And I explained why 1,000 is not just a number taken out of the air, it's the sort of lifespan that we could expect most of us to have if aging didn't exist. And if risks of death other than aging stayed the same as they are today, which of course again is a very pessimistic scenario. So I'm going to close just by talking a little bit about the social context of this. I give a lot of talks to general audiences, to people who are not necessarily technologists, not biologists, and I get a lot of blowback all the time. And as you probably know, I do a lot of media as well, and I get the most extraordinary reactions to all of this, mostly about whether it would be a good thing to actually defeat aging with medicine. Now, it just blows my mind that people would have a problem with that, but they do. And one thing that they forget, one thing that a lot of people forget, is that this is all about health. This is all about keeping people in a good state of health, and that any longevity benefits there might be as a result are as a result. They are a side effect of the good health. Once people get that, they get a little bit less concerned, because of course they don't want to live a long time in a bad state of health. And we really are talking not about being healthy for one's age, we're talking about truly, being able to keep up with your granddaughter on the dance floor, looking and feeling and functioning absolutely as well as you did in early adulthood, however long ago you happen to have been born. But I still get things like this. First of all, even if I say this to people, it goes in one ear and out the other, and they'll say, well, I wouldn't want to be old all that time. Then people will say, well, how long do I want to live? I don't want to live that long. What a stupid thing to say. I mean, how the hell are you supposed to know how long you want to live? It's like saying, it's like having an opinion about what time you want to go to the toilet next Sunday. You don't have an opinion about that because you're going to have better information on the topic nearer the time. Right? And it's exactly the same. I have no idea whether I want to live to 100, but I do know that I want to make the decision whether to live to 100 when I'm 99, rather than having that decision gradually removed from me by my declining health. You know, it blows my mind that people could be so stupid. And, you know, of course, there's a billion different objections based on, you know, social context of one sort or another. People say, well, you know, we're going to have too many people, aren't we? Or, you know, dictators are going to live forever, or how we pay the pensions and stuff like that. And, you know, I mean, again, it's just unbelievably stupid to say things like that, because, of course, this is going to be gradual. You know, we're still only going to be getting older at 1 year per year. Hello, we're not going to have any 1,000-year-old for 900 years, whatever happens, right? And, you know, in case you hadn't noticed, other things happen in the world rather quickly. You know, nobody has the faintest idea what the world's going to look like in 50 years. Nobody knows, for example, just to take one example, whether we're going to have nuclear fusion in 50 years. If we did, then clearly we'd have an option of using much less fossil fuels, having much lower carbon footprint, and having it be possible to have a lot more people on the planet without significant environmental consequences. You know, that's just one example. So, again, it's crazy. In fact, that's the reason why I think, the strongest reason why I think we have a very clear moral obligation to be doing this work, because the fact that we don't know what life's going to be like in the future means that we can't say that people won't want these therapies and they'll be better off without them. What we can say is that they are entitled to make the choice on the basis of the circumstances that they find themselves in, whether they've got technological solutions to problems that we might have foreseen, or whether they've got sociological solutions, just, for example, not wanting to have as many kids as we want to have, things like that. We have no idea. The bottom one, actually, is the one that annoys me the most. I mean, how selfish... I mean, when I speak to older audiences, I often say, OK, raise your hand, please. Everyone, raise your hand if you have a child. And most people raise their hands. And then I say, OK, put your hands down. Now raise your hand if you have a child and you don't give a damn about their welfare. You know, I mean, but people will actually be willing to say that it won't be in time for them and that's why they're not interested. Even in front of their own kids, they'll say that. You know, obviously no one would say something so selfish in any other context. And yet in this one, it's common. It's completely blatant. So what this tells me is that there's a real cognitive divide here. Have I got this? Let me just check. No, I haven't. I call it the pro-aging trance sometimes. That people just, like, they've made their peace with aging because they've grown up knowing that it's ghastly but also knowing that it's inevitable. And so they've had to engage in some kind of psychological self-manipulation in order to put it out of their minds and get on with their miserably short lives, you know, and make the best of it. And of course that makes perfect sense if the thing that's going to happen to them in the distant future actually is completely inevitable and there's nothing they can do about it. But now that we're not there anymore, now that we are within striking distance of seriously bringing aging under medical control, that attitude is a massive part of the problem. So if there's one thing I want to leave you with tonight, it's to understand that a lot of people don't think rationally about this thing, and they are slowing things down. The support that exists, whether publicly or commercially or even philanthropically, which is the main source of Sense Foundation support, the support that exists for all of this stuff at the moment is woefully inadequate. And it's causing progress to be made at a speed that I would estimate at about 1/3 in terms of scientific progress of what could be achieved with appropriate funding. And that's fundamentally because of this irrationality that people have, having made their peace with aging. So go out and make a war on aging, and we'll actually get somewhere faster. I want to remind you of this before I stop, the fact that aging is no fun. I want to mention this book that I referred to earlier on, which came out a few years ago, but you can still get it on Amazon. And it's written for an educated non-specialist. It doesn't rely on any jargon, but it is fairly heavy going, but you guys should be able to get through it with a bit of patience. It talks in gruesome detail about all of the various types of damage that I've referred to and the ways to fix them. And finally, of course, we have a website, we have an email address, and you're very welcome to get in touch whenever you like.